the slides are okay, and I will begin. Denis, can you see the slides? Okay, nice. So first of all, a couple of words about me and about today's topic. So my name is Maxim. I used to work for Circle, our today's host, and currently I work for BioCat, a pharmaceutical company in Russia, but I still, of course, have friends at Circle as well, and they invited me to give this talk, lecture about some internals of how Haskell works. So when usually people talk about Haskell, you see many discussions about type level stuff, about laziness, about correctness, and so on. But today we will focus on more on less known part on how it works on a real machine and how you can use this knowledge to optimize your code and achieve better performance. So this will be a very introductory level talk, and there are a lot of good materials on this topic on the internet. So I will try to give you a path you can follow using links provided in the end of my talk, and I hope to get you interested in this topic. So okay, so actually my talk, my slides is based on this wonderful presentation by someone named Takinobu. It is called GHC Illustrated for Hardware Persons. It's a large PDF with slides describing all of the internal details on how Haskell works on the real hardware. And it's constantly updated for new GHC versions. So when new GHC versions come up, for example, 8.10 lately, this PDF gets updated. So if you want to follow GHC development, you can use this excellent resource. And I took some parts of this presentation to illustrate a very introductory level of Haskell on real hardware. So let's begin with the compilation pipeline. GHC has a fairly complex pipeline on in its internals on how to transform Haskell code to assembly, to something that can actually run on your hardware. So we take our program in Haskell as an input. Later it gets translated into an auxiliary language called core, and this is the point where all optimizations happen. So core is a language that is easier than Haskell, but still simpler than Haskell, but still has a lot of features. But being simpler than Haskell, it allows to write optimizers more easily than for Haskell, which is usually called surface level syntax. And you can find a lot of materials on core on the internet, a lot of talks and blog posts, because it often makes a lot of sense to look at how core looks for your Haskell input code to understand what is going on. But this is not the final point. Core, a program in core optimized, one is translated into another language called STG, which is a functional language as well, but a lot more simpler one than core. Then STG is compiled into a language called CMM, C minus minus. This is like a, a high-level assembler, something like LLVM in spirit. And from this high-level assembler, you can compile to actual assembler of your target architecture. For example, Intel CPUs or ARM or anything you want. And the nice thing about GHC is that you can see how your program looks on each of these steps. You can pass options to GHC compiler, and you can see how your program gets transformed through this pipeline. For example, to see your program representation as core, you can use this flag called dump simple. Simple stands for simplifier, which means optimizer in Haskell. So you will see how your program looks after the optimizations. And then you can dump STG code, you can dump CMM code, and of course you can dump assembly code. There are also a couple of more useful flags to simplify reading these dumps. So first of all, you can redirect dump output to a file. Then you can suppress a lot of redundant information. Usually, you don't want to see this information when you are trying to understand core or STG code. And the last flag, suppress uniques, will suppress the generation of unique identifiers, and you will see your names for variables you used as you have them in your input Haskell program, and this will simplify your reading of this dumped code. So, as I said, there's a lot of material available on core online, but today in this talk, we will focus on these two parts, on STG and CMM. So let's begin with STG. STG stands for Spineless, Tagless, G machine. So what do these words mean for us? Actually, there are two important parts here. First is this part, machine. It means that STG language is a simple language with precisely defined operational semantics. In other words, there is a direct correspondence from STG code to what a machine would do with like registers, memory access, and so on. So this allows a direct translation from STG code to assembly code. And another word we will pay attention to is this one, tagless. And this simply means that all Haskell objects in our memory, in the heap, are represented uniformly in the same way. This will be important later on. STG was first described by in a paper by Simon Peyton Jones in '92, which introduced the Spineless Tagless G machine. It was built upon previous work on G machine and tagless G machine, and finally this one. And it was at the heart of GHC Haskell compiler forever since. And of course, this technique is still being improved. And actually, in 2007, it stopped being tagless. They introduced something called pointer tagging, but this is not relevant for today's talk. So let's take a look. Here I have a very simple Haskell function that takes an integer, squares it, and adds it to 5. Let's see how this function looks translated to STG. Here I have an output from GHC compiler for dumped STG representation for my function. I simplified the identifiers a bit to make them more understandable, but anyway, this is a dump from the compiler itself. What do we have here? Pay attention that we have let statements, and in STG, in STG semantics, as I said, it's directly related to what assembler does. Every let operation is a memory allocation. So in this concrete example, we allocate 2 memory cells. First one contains an integer, 5. Don't mind the sharp signs for now. And the second cell contains a lambda, a closure, a function that will square our number. And result of called bar is application of plus operator to 2 newly allocated cells, like to a closure which squares input number and to closure that contains the number 5. So to repeat, in machine representation, when an actual machine will be running this code, this is what will happen in sequence. First, we will allocate 1 cell with a number 5. Then we will allocate another cell containing a closure, executable code, and we will return another closure referring to those allocated cells. And now let's see how the same function gets compiled to STG when we enable optimization. Here I have the same dump from GHC, but I have enabled optimization, and we see that our function looks completely different from the previous slide. And here we see case statements. And in STG semantics, case statement is an evaluation. So the previous function just allocated some closures and returned reference to these closures. But this version is one big function closure which has code to evaluate its argument. So we evaluate x to get an integer that it has in itself. Then we apply primitive operation of multiplication for this number. So we get as an input a Haskell integer number. We evaluate it to extract its value because it itself may be a lazy value, a so-called thunk. And before we can do something useful with it, we must evaluate it. So we get input number, evaluate it, we multiply it, we square it, and we return our result without allocating any new value. So even if a straightforward translation from Haskell to core to STG will lead to a lot of allocation happening, the GHC optimizer is able to get rid of most of these allocations in most of simple cases, at least. So, for example, in this one, we got from 2 allocations to 0. And this function will only evaluate its argument, return a new result, and will not allocate any additional memory for temporal data. But of course, it's not always possible to avoid allocations at all. For example, in this function, I return a singleton list, and of course, I have to allocate it somewhere. And I have to store this value x multiplied by 2 somewhere. So in STG, it will look like this. We have a closure allocated with let, which evaluates x multiplied by 2, and we return a list constructor applied to 2 arguments, our closure and empty list. So as you may wonder, that we want to return a list of integers from this function, but we return a list constructor applied to a closure. And how is this possible? And this is directly related to our machine being tagless. It means that at this level, every object looks the same. So every Haskell object is just a heap object. And before doing something useful with it, we just evaluate every object in a very uniform way. And this is what Tagless in STG buys us. And now we will look at actual representation of these objects. So heap objects in Haskell consist of two parts. Header and payload. Header is constant for the objects. And a header contains an so-called info table. This is something, some static data that describes the type that is contained in this heap object. And entry code. What is entry code? It is an actual assembly code that is called each time you want to evaluate the value contained in this heap object. So, for example, for closures, for chunks, it's a code that evaluates them. And for already evaluated values, it's just a code that does nothing. But as I said, since we have a tagless machine, and initially they did not want to build custom logic to tell evaluated objects from chunks and so on. Every object has entry code, and it may just be returned, do nothing. And payload is specific for each type of objects, and it usually contains arguments to constructors and values captured by closures. So reference to other heap objects that are needed to run the code. And now let's see how some of the well-known Haskell types are represented as heap objects. This slide comes from the presentation I mentioned in the beginning. So if you have a Haskell character, it will have a header that refers to info table for this type character, and a payload, which is, in this case, a primitive value of type character. If we want to look at more complex types, for example, a list of integers, I have a list of two numbers, and for this I will need to have 3 heap objects, as in any linked list. And here you see that first cell is referring to the list constructor, the colon operator, and in its payload it has an int object similar to character on the previous slide, and reference to another heap object which represents the tail of our list, and so on. So this is a very nice representation for achieving uniform evaluation of values in our Haskell program. So now let's look how they are actually evaluated. Let's take our previous example, STG code for function that squares its argument and adds 5. I will take an optimized version for clarity. So this function is represented as a heap object of this structure. Its header refers to assembly code which does addition, because this is a result of last let statement. And in its payload, we have reference to two closures. One is a constructor for number 5, and another one is a closure that squares input number. When we apply this to a value, for example, to 2, we need a value of this x squared. So the evaluation, because we need to evaluate x squared, evaluation jumps to entry code for this closure. So here. Here we evaluate x squared, and actually we can override the closure in place. So now at the place where we had a function closure which squares a number, now we have just this number 4. The execution jumps to entry code for the whole function. Here we can do the addition and override the whole thing. So as you see, we have a result at the same place where we had a computation function bar applied to number 5, and the two closures that we allocated, auxiliary closures, are now not reachable, so they are considered garbage. And before you raise complaints, please remember that this is a very simplified presentation to give you the essence of what is going on. And if you want low-level details, I will give links at the end of my talk. Now, all of this, what I described, works for ordinary Haskell types. And these types are called boxed lifted types. And of course, in real Haskell, we have low-level stuff, where we can access these internals directly. And aside from boxed and lift types, we have unboxed and unlift. What does this mean? Boxed types mean that we represent them via a pointer to some memory location, for example, to a heap object. And lifted types are those that may contain the undefined value, or the same thing is usually called bottom value, but I will refer to it as undefined. So ordinary Haskell values are boxed and lifted. So they are always represented by a pointer, and they always may have a value of undefined. Of course, we may wonder what are other options. And the other extreme option is unboxed, unlifted type. And these are in the right bottom corner of this slide. These are usually primitive values like numbers, characters, and so on. Now, there are boxed unlifted types. For example, pointers to byte arrays. They are pointers, but they can't be undefined. So if we have a pointer to primitive byte array, it's always a pointer. But there are no lifted unboxed types because, well, unboxed type is just a value. You can't have a special undefined value in there. So this knowledge about boxed and unboxed types may sometimes be useful when you are doing magical optimization and you're writing low-level code, and dealing with unboxed types directly may come in handy, but I want to stress that in most everyday usage, GHC is able to optimize your code. And when you use boxed integers, for example, in your code, in actual code that runs, you will only get like unboxed integers, and no boxing will happen at all. So please go for this only when you are completely sure. For example, you have examined core and STG output and you know what you are doing. But anyway, it's very useful and nice to know how things work. But as a more useful demonstration, let's talk about data constructors. Here I have a data type, a pair of two values, and a function that gets an integer and constructs a pair of two new integers. Integer multiplied by 2 and integer plus 3. How does this look in STG representation? You see that this function does two allocations. It allocates a closure that will add a to 3, another closure that will add that will multiply a by 2, and it returns a p constructor applied to these closures. So when you construct, when you think you are putting like a multiplied by 2 into your structure, what actually happens, you are returning a constructor that remembers how to compute what you have put in it. And for example, if you are writing recursive functions, this usually happens with pairs, which are like this in Haskell. They store closures, or if you if you just have some long-living data that you are not using right away, you will have these closures referring to closures and so on. And this is usually not a nice thing for at least for typical business applications that works with JSON data and so on. So what happens if you mark these fields in your pair as strict? So here I have an SP data constructor and the same function, which puts two integers in there. Let's look at STG code. And here you see that in application of our constructor, we are referring to evaluated values. So function pair will evaluate its argument, evaluate its two integers you want, a multiplied by 2, a plus 3, and only after that it will put them into your structure and return to where it was called. So to summarize, it's a nice practice to make your data types, fields in your data types strict. And there is even an extension called strict data. You can enable this per file or in your cable file for the whole project. It will make all fields in all data constructors you are defining strict by default. And of course, there is an escape hatch. There is a way to make a field lazy when you have strict data extension enabled. So please refer to the documentation. Now, I have demonstrated that closures get rewritten and some closures may become garbage, so you don't have any reference to them. Of course, you need to collect this garbage. How exactly does this happen in Haskell? And to answer this question, we now finally turn to CMM. As I said, STG is practically in one-to-one correspondence with CMM assembly language. And let's see how CMM code looks for this STG code. So this is our familiar function, which multiplies its argument by 2 and returns a singleton list with that value. Now I will show you first lines of CMM code for this same function, and they look like this. So this is really close to like low-level C or even assembler code. And what do we want to see here actually? It's this thing. The very first thing when we enter our function foo, we do a check we check some HP value against some constant HP limit value, and if the check succeeds, we call a function called stg_jc fun. What does this mean? This is actually a check. Are we out of heap space? So every function in Haskell, when it starts evaluating, first of all, checks if there is enough heap space available for the closures it will allocate. So, for example, this function will allocate one closure, and it knows that its size is 48 bytes. You see on the previous line, like HP plus 48. And if it cannot allocate as much memory, it will call GC. So this is a further reminder that in Haskell we have like stop the world garbage collect. But why is it possible to get away with such a simple check? So like we compare two pointers, HP against HP limit. That's because of how very clever memory allocation works in GHC. In GHC, we have memory divided into multiple generations, usually two. First one is called the nursery. It's divided into two sub-generations, but that's not very important for now. And its default size is 1 megabyte per OS thread. So we have some data in this space, and HP pointer points to last occupied cell in this space, and HP limit pointer points to, well, where it ends. And new allocations are made simply by incrementing the HP pointer. So we take more and more cells until we reach the end of our heap space. What happens now is, as I said, we call garbage collector, and garbage collector will traverse our first generation. It will find live objects, indicated green circles in this slide, and it will transfer them to a new generation. Now, after that, HP pointer is rewound to the beginning of our heap, and we can start allocating again. So after GHC is done, we jump back to where it was called. Now the nursery is empty, and the thread can allocate more and more data it wants. So a nice consequence of this algorithm is that we do not need to touch dead data at all. So the less live data you have in your heap, the more fast will be garbage collection. And this is described by a generation hypothesis, a preposition on which this algorithm is based. So if an object was born lately, it will die soon. So most data will not survive the first garbage collection. They will die in nursery, and there is no problem with that. However, there is one slight problem in this algorithm. Previously, we talked only about immutable Haskell values. So, for example, in this slide, we can have objects in zero generation in nursery referring to other objects in zero generation, and we have objects in zero generation refer to objects in first generation, and of course in first to first. And because objects in the zero generation were born after objects in the first generation, if we don't have mutation, we don't need to look at all at the first generation when we are collecting the first one, the zeroth one. But in Haskell, we can mutate. And by mutation, when we mutate an object that lives in the old generation, we may introduce a special link from the old generation to the new one. and our algorithm will fail because this green circle does not have references in the first generation, and if we do not look at the second one, we will collect it as garbage and break this link. So when you are doing mutations, for example, via IUREFs, MVARs, STM, like this, Haskell has to keep track of what objects are mutable in the old generation, and GC will have to traverse these objects as well. So if you have a lot of mutable data in the old generation, even if you're not mutating it, but if it just lives there, if you're not mutating it often, it may slow down the garbage collection. Of course, it's not as simple as I described, and there are some optimizations, for example, for mutable mutable arrays, and this slowdown does not scale linearly with the array size. It's better than that, but still there is such a trade-off. Now I will want to show you an example of how nursery size affects the performance of your program. Remember, I said that default nursery size in GHC is 1 megabyte. So what happens if you are allocating a lot of objects is that garbage collections will have to happen often. Let's take this code. This is Haskell, not STG or CMM. What this does, it allocates a long list. And if we write a program to that allocates this list and then prints it, we may analyze how it performs. Here I have a graph produced by thread-scroll program, which shows activity of our program over time. And this pink portions here is where our program does useful work. So in this case, where it allocates new cells of our list. And these blue points, blue lines, is when a GC happens. So as you see, these default settings, nursery size of 1 megabyte, there are a lot of garbage collections. And this runs for a considerable amount of time. And this part is simply where it's printed, and there are no garbage collections in there. So if we look at runtime statistics for our program, we see that we are doing almost 200 minor garbage collections in the first generation. And usually, this is not a good sign. So what will happen if we increase the size of our nursery? This option, RTS flag, I will set it to 64 megabytes. And you see that there are practically no garbage collections in the first part of our program. We just go and allocate everything we want, then we print, and then we garbage collect. So statistics confirms that there is only one minor collection and two major collections. If we were to increase nursery size even more, for example, set it to 256 megabytes, we won't have a single minor collection. But of course, there's a trade-off between number of collections, their time, and so on. And usually, it's recommended to try 64 megabytes. If it doesn't work for you, you have to analyze graphs, analyze statistics, and tweak this value for maximum performance at your concrete use case. But just try starting with 64 megabytes and see if it gets better. By the way, GHC is a program in Haskell, and therefore it suffers from the same problem. So you may try running GHC with this option, and in most cases, it will compile your code faster, especially if you are using some kind of parallelization in like you're running GHC with like J and number of processes. And here's the last topic I want to describe today. So evaluation in Haskell is a CPU work. So you multiply some numbers, you to this, to that, arithmetics, and this is highly parallelizable by physical cores. On the other hand, garbage collection, by its nature, is a lot of memory accesses. So how does this map to a layout of your processor? When you have a multi-core processor, each core has its own access to memory. And if GHC, if garbage collection runs in parallel, theoretically, GHC threads running on two different cores do not clash with each other, multi-core setup. But there is this wonderful technology by Intel called hyperthreading. And hyperthreading is like two virtual CPU cores in one. And the major difference is that these two cores have only a single channel to memory. And of course, Haskell does not know this. And if it will run two GHC threads on this virtual CPU cores, it will be too slow because they will compete for the same channel to memory. So if you have a CPU with hyperthreading, you either want to disable it completely or limit number of garbage collection threads to number of physical cores, not virtual ones. And I promise a last point for today, a very practical advice. Let's see what happens in this simple program. We allocate a huge list, and then we sleep. So what do we expect? We expect that we do some work, and then we stop, and nothing will happen. But actually, if we look at a graph from ThreadScope, we will see that between two parts where we are allocating, we have GC running, and this is called idle garbage collection in Haskell. When Haskell notices that we are doing nothing, it will run a garbage collection just in case every 300 milliseconds. And let's imagine that your program is a web server, and naturally, you can't predict when requests come to your web server. And if it happens that there were no requests, and then idle GC starts running, it stops evaluation. And at this point, a user hits your server, and it will wait. So for applications like web servers, it is practical to disable idle GC completely because it only gets in the way. So to summarize, it's advised to use these runtime options to increase the size of nursery to 64 megabytes, for example, to make minor collections less frequent. Then there is this separate thing called heap for large objects. And in contrary to usual nursery, which is one per each physical thread, this large object heap is shared between all threads. So when you start having a lot of threads, they will compete for this large object heap if you have large objects. So it makes sense to increase it for linearly by number of threads you're running. Then you disable idle GC, and the last flag, QN, sets how much threads can GC use. For example, if you have a hyper-threading CPU with 8 virtual cores and only 4 real ones, you may want to use 8 threads for evaluation, but only 4 threads for garbage collection. Okay, I hope this was at least interesting as a gateway drug to understanding how Haskell works. Here are some very useful links that I used to prepare this talk. And of course, I will to make this presentation available via, I don't know, Twitter or something like this. And you can see for yourself how really hard it is in the real world. And I mentioned this tool called ThreadScope and other methods for profiling what happens in your Haskell code. And this is also described in various places online. But I am preparing a new blog post on this topic, and hopefully sometime soon I will post a comprehensive guide to profile and identify various types of performance problems in your Haskell program. So stay tuned. Thanks for watching. And now I think I'm ready to answer some questions if there are only. Are there questions that were not answered by anyone? Let's see. There was some questions regarding details of STG syntax, and I did not want to get into that because it's not related to our talk. And thanks to my colleague Vlad for answering these questions. Yes, there's a question how closures are written in a multi-thread environment, and a high-level answer is that there is a kind of locking mechanism. If one thread starts evaluating a closure, it will lock it, and other thread, if it wants a value of the same closure, will just wait. And this is called black holing, and also is described in papers and GHC source code. Okay, another question about syntax. Yes, less minor corrections doesn't mean faster. Actually, in example I was showing, if you paid attention to the timeline, running time for this program was practically the same. But in a real environment, it can have a great difference. It depends on your workload. Okay. So
there was a question about inlining that I think you skipped. It was about like what stage does inlining happen at?
Yes, inlining happens. All optimization happen on core step. So let's take a step back. When you have your Haskell syntax, first thing that happens is to type check it, because you generally want your errors from type checking to refer to the code you wrote. So you don't want to see type check errors returned with locations referring to some code in core. So first of all, it's type checked. Then it's translated to core. This is a simple operation, translation from Haskell to core. And then this gets optimized. This code in core, which was obtained from type checked Haskell, is well, it's known that it's correct because it was translated from type checked Haskell. It's optimized at this step. You apply so-called core-to-core transformations, and via various dump flags, you can actually see each step that happens. So, like something gets invite, some rules apply, like some bindings float out because of some common sub-expression elimination happens, and so on. And when this optimization pipeline finishes, you have optimized core that is later translated almost mechanically, as far as I know, to STG. So, and after this step, practically no big optimizations will happen. So to summarize, all interesting important optimizations happen on this core-to-core step. I believe there are a couple of talks on this pipeline by Vitaly Brigilevsky. You can see, you can try to find them online. I think he he explains this a bit better than I do. So I hope I answered the question. Moving on to Pavel Schultz's question about stopping the vote. Yes, thanks to Maxim Koltsov for answering. I will repeat that. Yes, it stops all threads. So when one thread hits its limit and wants to do garbage collection, it calls this STG GHC fun. It will then ask other threads to stop what they are doing. This moment is called GHC synchronization. So all threads will wait to stop, and then GHC will run. GHC garbage collection in GHC is highly customizable. You can set number of generations. You can even have like only one generation. You can set limits for nursery, limit for total heap size, and you can enable compaction garbage collection for all generations. So I did not say this, but all generation by default is allowed to grow infinitely, and if you want to limit your heap size, you enable so-called compacting garbage collection, which will keep the heap size constant, but of course it will kill your program when it overflows. And there is new work in progress GHC garbage collection introduced in GHC 8.10 by well-typed, as far as I remember. There are talks by Ben Gamari on YouTube, you can see. This is an attempt to make parallel garbage collection. So they tried to make minor collector non-stop the world. So or major collector, I do not remember at this moment, but it is there is hope to avoid stopping like the world. So you can read about this in well-typed blog and in GHC manual. It's already in there for the latest version. So next question about thread scope. Yes, it dumps a lot of data into a file. It's called an event log. It's a mechanism built in GHC that is able to dump a lot of useful information about what happens in your program. And in my experience, it's not as costly as you would think. So it's a log in binary format, and you can just enable it, and it won't slow down your program as much. At least not as much as when you enable more hardcore mechanisms like heap profiling or cost center profiling. Like this will slow down a lot, but event log dumping is not as bad. Regarding the last part of the question, can this file be opened in runtime? I don't know. That's a very honest question, honest answer I can give. You would have to research this. a question by Nick Linker about mutable objects. So does this mean that computations in ST monad will never be as fast as imperative code in C++ or Rust? Well, if you manage to stay in the first generation, so you want it will be it should be as fast. And moreover, GHC will often compile this code to tight assembler loops that practically don't allocate anything. They will just like do some arithmetics in registers and jump without allocating new closures. It's very clever techniques employed in core. So, for example, you may think about core as like functional language with goto, practically. So please don't take my words too seriously. Okay. Why did STG code retain reference to type classes, not only primitive operations? Because that was code I was showing. The code I was showing was not optimized version. Of course, because I disabled all optimizations. If you enable them, these type classes will get inlined and you will use primitive operations. Objects either leave short. I can, regarding second question from Pavel, I can't say for GVM because I did not research how GVM does its garbage collection, so I'm not qualified to answer that. Is it possible to observe multiple threads in the profiler? Yes. The thread scope application gives you breakdown by physical threads, by OS, like POSIX threads. And if you want even more granularity, if you want to see what Haskell green threads are doing, there is a tool called GHC Events Analyze by well-typed. Maybe I had the link in my slides, maybe I didn't, but I will have a link in my blog post anyway. Yes, short answer is it is possible to see how different threads perform during execution of your program. Yes, that is the thing that you post in the chat. What will be the next step to learn more? Well, I would say that depends on what you want to learn. For me, a very enlightening reading was the original STG paper by Simon Peyton Jones. It's a very big paper, but you only want to read like first part of it, where the high-level design of this stuff is described. It really explains this stuff in a nice level of detail. But I believe this is. Would you want to collaborate on suspected GHC RTS GC bug? Well, I did not ever touch GHC code itself, but at this point I may advertise that there is a team of people at ZeroKel working full-time on fixing GHC bugs and introducing new features. So if you want your bug fixed, maybe you can you just tag ZeroKel in Twitter. How did I create the animations? It's just Keynote on Mac, nothing too fancy in this. So if there are no sorry, Kirill, I do not know how to answer this question. So there's a question about details of STG syntax. What is the difference between updatable and reentrant closures? And for this, I would just refer you to papers and the documentation. So, thanks for watching. I hope you enjoyed this hour we spent together. You can always find me on Twitter. I believe the Circle will do a new tweet with my slides, recording, and so on. So by all means, good luck, and well, let's make Haskell great forever. Thank you.